Okay, let's continue with the final short bit in which I would like to sort of give some current research directions and open research problems. So first I would like to advertise a bit some work we did in Nijmegen, we call Automata Wiki. I think for every mature field it is important to have a good set collection of benchmarks. And my experience is that for a long time there was not such a good collection for both model-based testing of finite state machines and for the automata learning approaches. And by now we see that there are dozens of different learning algorithms. I outlined a bit the L-star algorithm, but different authors have proposed different algorithms which perform better in certain cases, maybe not so good in other cases. We also have dozens of conformance testing algorithms. So we thought it would be good to collect our benchmarks. And so here, this is the website. And what you see is we have a lot of mealy machine benchmarks. For trivial things like a coffee machine toy example, but also for some of the banking cards. So if you click here, you get a description of the benchmark, and so then here the actual state machine models for a number of different bank cards, Maestro, MasterCard. So we have by now hundreds of benchmarks collected on this site, and the idea is that when people come with new learning algorithms or new testing algorithms, they can use this. And so it's a wiki, so basically everybody can add models. So if you have some new state machine, please add it. I think that's a good opportunity to make the field more mature. Okay. So what are we working on right now? So these active automata learning algorithms perform pretty well on many case studies, but there are limitations. There were questions, I think, about timing. That is an issue, we're working on that. But a key problem often is the size of the state machines. If state machines of up to a few thousand states we can learn, but if it gets bigger, we are out of business. So then one of the things which you can try to do is to exploit the structure that is present in your system, the system that you want to learn. This is the same way which model checking researchers have advanced the field by continuously for 25 years or so, sort of look at, okay, what is the structure in state machine models that we can explore to fully sort of visit all the states of the model. So people have been looking at partial order reductions, BDDs, and so on. And then we were looking at similar things for model learning. So here is one example of a little case study my student Joshua Moerman did. So suppose we want to learn a model of a system M, which behaves like a Moore machine. So a Moore machine is like a Mealy machine, but now outputs are visible on the states. Actually, he wrote it down for Moore machines, but he could also have done the same work for Mealy machines. Okay, so suppose we have a Moore machine which jumps from one state to another based on inputs. And in every state, it produces two outputs, O1 and O2. Then we can actually sort of view this Moore machine as a composition of two Moore machines that are composed in parallel, which both share the same input, and one outputs O1 and the other outputs O2. Yeah, so here is an example from a paper from Ravest and Shapir. So here we have a Moore machine which models a simple sort of register machine. So the state of this register machine is determined by n Boolean values, which are stored on a tape. And then there is a head which may move. And so there are three input actions. You can do an L, and then the head moves to the left cyclically. You can give an R, then the head moves to the right cyclically. And you can give an input F, and then the current bit, the bit where the head is right now, is being flipped. So this is a trivial system, but the number of states, of course, is pretty high because any bit can have any value. So we have 2 to the power n times n states because we also have to record the position of the head. So learning this by a regular L-star algorithm will be problematic, but of course there's structure. So my student had a paper where he had some nice smart algorithm to exploit product structure, but then he also had sort of an obvious algorithm where you just keep in sort of a cache previous queries, because for all these different, if you write this complicated Moore machine as a parallel composition of n Moore machines, then the queries you get for different machines will be very similar and often the same. So by just caching the queries in a smart way, a very straightforward implementation, my student was able to get superior results when compared with the TTT algorithm, which is the state-of-the-art active learning algorithm thus far. And so the benchmarks he did was these. This is this counter machine. This is this n-bit register machine. So for different parameters, and you see that the number of input symbols is really much lower when you use this simple trick. Now it turned out there some people did work on benchmarks. So from quite a while ago there were benchmarks for circuits being described as Moore machines. And so he also tried the same approach there. And then, well, of course, this register machine really is completely decomposable in parallel. So it's a perfect example for applying a decomposition, but also for realistic circuits. In many cases, using this trick, my student was able to outperform the state-of-the-art learning algorithms, but not for all. It's a more diverse image. But I think there is still a lot of room for sort of explaining learning algorithms, that there is some structure in the system and then exploiting that structure. For instance, there is nice work by Abel and Reinecke, which studies a situation where the system is composed of a serial composition of 2 Mealy machines. So the output of one Mealy machine acts as input for a second Mealy machine, and then they consider a setting where you know the first Mealy machine, but you have to infer the second one. And so that's also a situation where you can only interact with the composite, but you know you have some information about the structure of the system which you can exploit. Well, a major source of state explosions is, of course, data parameters, because those will lead to many inputs. And so an extension of finite automata that has been widely studied in the literature is the extension of register automata. So a register automaton is basically a finite state machine, but now the actions carry a parameter, formal parameter p, and the values that you receive may be stored in a register. And when you do transitions, you may test for equality or inequality of registers. So no operations are allowed, but you can test for equality. There are still many systems which can be modeled in this way, because there are many protocols which sort of send data from A to B. And they don't perform operations on data. Or there are protocols where each process has a unique identifier, and the only thing that matters is that you have a unique identifier. You don't perform operations on it. Okay, so if we have such a model, then it turns out that the existing L star algorithm can be generalized, and there are various ways in which people have done it. And this is, for this extension, tools are available. And in fact, we can do slightly more than just testing for equality. So people have implemented extensions indeed with sort of, where data values are natural numbers and you can test for equality. But there are also extensions where parameters can be real numbers, and you can have tests for inequality, less than. So they're completely automated learning algorithms for these automata. We developed one such algorithm at Radboud University, Tomte, using an entirely different approach. There was LearnLib support, learning the same class of systems, so also with natural numbers and equality. And then there is an extension developed largely at Uppsala and Dortmund, but with recent extensions from Nijmegen, where we study richer languages. So, Volkhauer from Dortmund and my student Paul Vitero did a case study that was published in 2017 on the TCP protocol, where they really dealt with sort of this issue of windows that are managed by TCP. So you have sequence numbers, and if a sequence number falls into a certain range, a certain window, you get one behavior, and if it falls outside that window, you get a different behavior. So they implemented a version of our ALIP, which is able to deal with these register automata and these the basic predicates that you need to be able to deal with these windows. And they were able to learn this model, which is a very simple model, but actually this model demonstrates a standard violation in the Linux implementation of TCP, which was led to a change of the implementation, which is sort of cool that there's so many Linux implementations out there, and all of them have been touched by this little result of my student. So that's the positive thing. So, okay, model learning is very effective, but there are serious scalability results. So to get this result for TCP, we had to work really hard to extend the RALib tool, which is not trivial, and if you add one other operation on data, you have to start from scratch. And this is difficult, and also, so just to learn this little state machine, huge numbers of queries were needed. So this is a result of 2 days of doing learning queries.
To learn these constraints, do you use kind of a linear regression of some sort? How do you learn? So you of course learn the concrete constraints. How do you generalize it into abstract?
Yeah, so basically what our ALIP does is that it deals with abstract patterns of inputs, and then given an abstract pattern, it sort of computes a complete decision tree. Okay, if my parameter falls in this window, I observe that behavior. If it is below, then I observe that behavior. So it computes sort of a decision tree. And this decision tree is, of course, computed by doing repeated experiments to try all different branches in the decision tree. And then they use a constraint solver to get concrete values that ensure that a certain path in the decision tree is being taken.
But you know that your constraints are interval paths. So
Exactly. Yeah. Now we come back to this question that I mentioned at the beginning, this physicist which says, okay, why are you using a black box, whereas all the information you need is inside and you can just access it? And so we are looking for extensions of our approach where we can use this white box information, but in a completely automatic way. Which is not dependent on knowledge of the specific programming language or whatever which is used. And we have a couple of examples where we do this and actually quite effective. So one idea is to use fuzzy. So there is this wonderful tool, the American Fuzzy Lab tool, which is being used by hackers. Okay, let's use it as well. So basically, what it does, it sort of sends various inputs to a piece of software, and then it instruments the code and it checks whether certain branches in the executable are taken or not. And then it tries to compute if there are certain branches which are not taken. It slightly tries to modify the input to drive the system to these branches. And so it is using some genetic algorithm to sort of maximize the number of branches in the executable that are being visited. So this is very useful information because this AFL produces interesting input sequences for our software, input sequences that sort of exercise all or a large fraction of the branches in the executable. So we can use that using learning in a very simple way, because when our learning algorithm has produced an hypothesis, I remember the difficult challenge was to find a counterexample for this hypothesis. And the examples produced by AFL, the Fuzzy Lob tool, are just smart examples which try really different types of behaviors. So using sort of a combination of existing conformance testing algorithms and this Fuzzy Lob tool, we were able to win a competition in 2016 where it had a goal was to learn complicated state machines. And which is very natural because we get good counterexamples. But yeah, we want to go further. So the limitation of these register automata that you only can test for equality of data values or whether they're in the window or not, but you don't have operations on data, that's very restrictive. So my ambition is to really help industry with refactoring complex legacy code. And in this legacy code, of course, you have more complicated data types and operations on data. So one approach we are exploring right now is called tainting. So tainting is also an existing technique which is widely used by people from the security domain, but also in different areas. And to explain what tainting is, let me use an analogy. So suppose we have an ant nest, and we sort of want to figure out what the internal structure is of this ant nest. Then what we could do is take a little bit of paint and sort of paint an ant which enters here. And then the paint is sort of wet, and we know that if an ant greets another ant, they sort of, I don't know, they shake hands or whatever. Then some paint goes from one end to the other. So if the painted ant enters here, and then here another painted ant comes out, we know they must have been in touch. It may be the same ant even. Okay, so this is basically what is happening with tainting. What you do in tainting is you instrument the code, and so from every value you make a little object. So you record exactly what happens with the value when it is being processed by the code. So when values, you have an algorithm with two inputs, 2, and an output 4 is produced, then it could be the sum of the two inputs, it could be the product of the two inputs, it could be the product of the first input with itself, right? But if we have tainted these values, then if something comes out, we just have the information, okay, this is the product of the first input with the second input. And so this is the information which tainting tools provide. They sort of track what happens to values, and they give you information about the tests that have been carried out, the guards that have been evaluated, involving other input parameters of the system. So, there are lots of implementations of taint analysis, dozens of tools. We decided at some point to use a tool from the group of Andreas Zeller, which is written in Python, and so it applies to Python programs, and we applied that, and basically what we could do is to perform this tainting. So when we have certain input values, they get a color, so to say, and when output values occur, these output values are also colored, and we can see on the way the tests that are being performed. So the green value is compared to the red value, and because they were equal, you took the branch that you took. So that's very useful, and it leads possibly to an exponential gain in learning, because this combination lock scenario now no longer exists, because we can just see exactly which tests are being carried out. And so if they say, no, that we don't open the lock because the first value was different from 1, then we do another test where the first value is equal to 1. And then maybe the combination lock doesn't open, but then we have information about the second value. And by a small number of experiments, then we can sort of compute the whole state machine. So we are now exploring various approaches where we use tainting to learn extensional models of systems with data. And this approach basically generalizes to much richer class. So one student wrote a prototype where basically he used the RALib tool from Dortmund, but he sort of replaced one component, the tree oracle. And the tree oracle is the component which, given an abstract sequence of inputs, computes this decision tree. And that now can be done using tainting. Okay. Let's see. I think I want to move to conclusions. Oops. So I think this is a wonderful area. So automata learning is slowly becoming a standard tool for software engineers. And very frequently now I get emails of groups who use it to learn some model of a protocol or try to use it for refactoring. And clearly a lot of research is needed to make this into a mature technique, but we sort of know what we are doing, and I think the situation is very similar as with model checking. So now we are in sort of early stage, but if we continue for 10 more years to make it more practical, then it will be a standard tool, standard technique in industry. So that's really nice. And there's nice room for theory. I presented one Galois connection in my presentation today, but actually Galois connections are all over the place in automata learning. That every day I run into a new one, so they are useful. Future work, improved black box learning algorithms and testing algorithms, using these Galois connections to make learning more efficient. We want to go from Mealy machines where inputs and outputs have to alternate to richer settings where one input may not lead to any output at all, or maybe to 7 outputs, or sometimes to 7 outputs and sometimes to no output. We want to explore these combinations of black box and white box learning at timers, at probabilities. And for my group, the main application domain now is refactoring of software. So protocols were sort of nice, but I can't get research grants if I find bugs in protocols. If I'm lucky, I get a thank you message from some software engineer in the US. But I think that the technique has been demonstrated there. The real challenges are with legacy software, and of course, if we can do that, then immediately you could also think of having a startup company and really making this into something which has practical relevance. Okay, so that was it. Thank you very much.
You have a couple of minutes for questions.
Is there any approach that maybe I should for a moment? We have a system, and we know some of the components. Some of its components is known to us. And is there any approach to, and we do not the structure of and how they are composed, the architecture of the software? Is there an approach to find out to learn the model of the system?
You mean the structure of the components?
No, I mean that suppose we are going to learn a system that some of its components are known to us.
Yeah, okay.
I mean, we are not completely white, but we are somehow gray. But in this gray, we do not know the structure of the system, and we do not know the architecture and how they are composed.
Yeah. So typically in model learning, what we try to do is to sort of get a test harness around the individual local components, and then learn those one by one, and then we know by composing all these models how the behavior of the full system. But sometimes that's not possible, it's not practical, right? We can only access the system at the top level interface. We know that there are certain components in the system, but we cannot access all the components individually. So, one example of work which addressed this problem I mentioned, and the work by Abel and Reinecke on learning serial compositions of Mealy machines. That's a typical gray box scenario. But there's lots of work to be done there for more complicated systems. And so there is this nice work by Tiziano Villa and some other people on equation solving in process algebra. So when you know that you have a system C, which is A parallel X, find X. That type of theory seems to be very relevant for these problems, but there's lots of open work when it comes to learning.
Does this equation solving relate to prime decomposition, for example, what Milner did for CCS, or is it a different?
No, prime decomposition is very specific. No, this is more like you know that there is this component C and there's a component X, and you sort of know how they interact, but then, yeah, solve X. I can show you, point you at some literature. And, there's a bachelor student who recently also worked on this topic.
There is a related area called embedded testing. So you want to quotient the effect of the surrounding components to find out what the behavior of the component inside is.
Yeah, that's clearly also very related. Yeah.
There is a volume of LNCS about that embedded testing, and we have done some work. Any other questions? Sure. If there are no questions, just an organization reminder. Please fill in the evaluation forms for today and hand them into the reception. And let's thank Fritz for this wonderful tutorial.